This week we'll be covering Unit 3 of the Hugging Face course. It's starting to get way more interesting now. So the topic for this week is deep Q learning, and I really like their example that they have on the actual course of all the different environments and agents people have built. Uh, for this week, there's the Space Invader um, environment, but they you can do Pong. Basically, all of these Atari games are environments that you can train your agent in, and it's like a huge throwback to like people would like go play these games at the arcade, and that'd be like the big whole like a huge event. But now today, like people can create robots, machine learning and reinforcement learning agents that can go beat these games without any human input. And it's cool that that capability is in our hands now, especially if you went through this week's course, which was a pretty light material compared to last week. So the big jump from last week, which was regular Q learning, we are now introducing the deep Q learning, which basically means we are now using neural nets. So the reason you would want to use a neural net for training an agent is comparing it to last week's unit. The training environment was very small. There was the frozen lake and the taxi cab environment. Both the frozen lake had a 4x4 frame, so that's only 16 states. But the taxi one had a few more. I think it was only 50 though, like 5x10. But in Atari, the amount of states and actions you can take in all of those different states is crazy. This is the number right here. It's 256 to the 10,0800, 100,800. So insanely huge number. And the quick reference is that there's only 10 to the 80 atoms in the universe. So there are more action state pairs in Atari than there are atoms in the universe, which kind of puts things into perspective. On this slide, we have the actual diagram for how Q learning is different from deep Q learning. In Q learning, you have the state and action, which these values are going to be inserted in a Q table, where we train using a Q function this table to have optimal Q values. Whereas in deep Q learning, we take the state, we throw it through a deep Q neural net, and we have these estimations for value actions from that state. So the big thing is here we use this table. They consider Q learning a tabular algorithm because you can put the data type in a table/array, but for deep Q learning, since we are introducing convolutional neural nets and we're dealing with tuples now, so different data structure, we have to use a different format to store this data type. So the deep Q network, DQN, how they call it, you take an input of 4 frames. They call it a stack of 4 frames. And this is passed through the network as a state and outputs a vector of Q values. So the diagram shows this pretty well. You have the stack of 4 frames. It'll go through a convolutional layer. Then it goes to fully connected layers and outputs Q value left, Q value right, Q value shoot. That's for this Space Invader example. You can kind of see it. You can only go left and right in this environment. You can only shoot. So not too many actions, but there's still, because of that state space that we had talked about, there are still too many state action pairs to use a table. So we output a vector of Q values for each possible action at that state. Then, like with Q learning, we just need to use our epsilon greedy policy to select which action to take. Then, when the neural network is initialized, the Q value estimation is terrible. Similar to how when we're doing regular Q learning, we initialize our table with just 0 values and then go through a training episode, update the values as we take actions. It's a similar idea where the beginning of the Q value estimation at the beginning is terrible. They describe it as terrible and non-zero because you can add some values, um, but during training, DeepQ Network Agent will associate a situation with the appropriate action and learn to play the game well. So the actual process to do this requires you to pre-process the input, and there's this concept of temporal limitation. So you can see that 160 like dimensions to consider, states to consider in this y-axis, 210 to consider in this x-axis, and they have this 3-step kind of time. This is kind of showing different like frames, but we're going to reduce that for both the training purposes to make the training much faster. We're going to reduce that to 84 by 84 state, since a lot of these actual states are never used in training and have no impact. Plus, you can see that over here we have color on the left side, but on the right side we grayscale it, and we use 4 temporal states instead of the 3. I'm not sure where the 3 comes from, but let me just review. We reduce the state space to 84 by 84 and grayscale it. And we do this since the colors in Atari environments don't add important information. And this is a big improvement since we reduce our 3 color channels RGB to 1. So there's less different types of data that our convolutional neural net will be selecting slash like parsing out some useful actionable data from, because we no longer have to worry about color. We don't have to worry about the unused space. We also crop a part of the screen in some games if it does not contain important information. Then we stack 4 frames together. So you may be wondering, why do we do the 4 frames? And it's from that concept of temporal limitation. If we only used one single frame, that doesn't give us enough information for kind of like direction, movement, velocity. But in this Pong example, even just having these 3 frames, we can see that this dot is in the middle. The dot is a little bit more to the right, and over here it is clearly to the right, and these are 3 different frames. So this stack of 3 would give a neural net enough information to make that determination that the ball is going to the right. And then from there, it'll estimate and either come up with a random action or take an action that is in the neural net for that specific state. So the state would be like ball is going to the right, but is also going like straight down or something. Like maybe you can detect some deviation in this y-axis, and it'll then cause take the action of either going up or down in this Pong environment. So what's a convolutional neural network? Part of this course assumes that you've gone through some base knowledge in deep learning, but I've found that the deep learning knowledge is not terribly important. Just purely definition-wise, the convolutional neural network slash CNN is a type of artificial neural network that uses convolutional layers to filter inputs for useful information. So in this diagram, you can kind of see that you'll take one kernel, this little section, and it'll be put into a feature map, and from there you'll get another input, and it'll go to the next step. Another input goes to the next step, and it'll these layers will add up, and then you will flatten them. That's kind of how this works under the hood, and there's a bunch of values, mathematical values associated with each step, and at the end, you like it would take like a class in like statistics, specifically for neural nets to really understand what's going on. But the output from all this processing in a convolutional neural network is like this zero point 0.2 weight for Donald, 0.1 for Goofy, 0.7 for Tweety. So I guess the example in this diagram is image classification. So because you take and analyze each pixel, what is the color, where's that pixel in relation to these other pixels? These are all of these different layers in the feature map where we're in this feature extraction uh, process, and we then classify it and assign this probabilistic distribution at the end. So that's like high level what a convolutional neural network is, and it's the type of neural net that we use to train our Atari game. We are now introduced to the DeepQ learning algorithm, which looks pretty complicated, but I really like how Hugging Face breaks it down and describes what the actual difference is at the bottom. So in deep Q learning, we create a loss function that compares our Q value prediction in the Q target and uses gradient descent to update the weights of our deep Q network to approximate our Q values better. So like after going through the course, I'll need to look up the definitions for a lot of the terms. I know that gradient descent is uh, kind of like that concept of decay from the last example, but using more math. Um, but the formula kind of looks the same as the last regular Q learning formula. So new Q value estimation is derived from former Q value estimation plus the learning rate times the immediate reward plus the discounted estimate optimal Q value of the next state. And this term itself is the temporal difference target. And we subtract that from the former Q value estimation, and the entirety of this bracketed expression is called the temporal difference error. So for me personally, I'll have to review this a little bit more till it sticks. But in practice, you kind of just use this formula, plug it in our hyperparameters that we'll be assigning in the actual course, in the actual hands-on Google Colab notebook, and then just running this using GPU acceleration. So this is the math under the hood. Another important concept is that there's two phases in training a deep Q learning algorithm. There's the sampling phase, where we perform actions and store the observed experienced tuples in a replay memory. And there's the training phase, where you select a small batch of tuples randomly and learn from this batch using a gradient descent update step. So this is compared to the regular Q learning algorithm. This is how we conduct training with deep Q learning. You do sampling plus training. And one of the last important topics from the material is this idea of deep Q learning training might suffer from instability. So because you're combining a nonlinear Q value function, a neural network, and bootstrapping when we update targets with existing estimates and not an actual complete return. Kind of like to put this succinctly is that deep Q learning suffers from having a whole bunch of different variables that are taken into account. We saw that the state action space is gigantic for the environments that you would use a deep Q learning algorithm. So you would suffer from that problem of having all of these different actions to take. Kind of like how humans sometimes have anxiety. Maybe they're like analysis by paralysis because there's just so many different actions you can take. The same is true for like these reinforcement learning algorithms, and specifically deep Q learning. There's just so many actions you can take that maybe the agent can be confused, and you can have like some kind of like catastrophic error at the beginning of your training run. Um, but there are three different strategies that we implement to stabilize the training. So the first one is experience replay to make more efficient use of experiences. We have fixed Q target to stabilize the training, and we have double deep Q learning to handle the problem of overestimation of Q values. So they in the material itself, they have good examples of what all of these means, but it is pretty in-depth material. So if I just go and show it really quickly, a lot of it is related to the actual algorithm itself. So this entirety is the deep Q learning algorithm kind of written out. So um, more so pay attention to this stuff for like understanding the vocabulary and understanding what um, settings you need to tune in your hyperparameters when you're actually training the agent in practice. So um, with that, that is the majority of like the information that I got from this course this week. There's only three main sections: the from Q learning to deep Q learning, the deep Q network, and the deep Q algorithm. So before moving on, do we have any questions?
Maybe please on the section that you showed, the states on your
Yeah.
slide. I forgot where to go. On this one, yeah, no, next, yeah, on this one. How is this number 160 by 210? Is this like a pixel length? Is that
Yeah,
what it
I
is?
think it's pixels, or it's just like different. It's like how many states there are in this x or this y-axis, how many states are on this x-axis, and it like they're different. Like I think they're pixels. I can't say for sure, but um they just call it the state space. So they reduce the space to 84 by 84. So the state space in this left example has 160 in this up direction, and then 210 in this right direction. So I don't know if it's pixels per se, but it's like just the states. Um, Kind of like the
Okay.
frozen lake area state was very small. Let me go see if I can. So like in this environment, there's like two states up and then three states right. So in total, six states that you pay attention to, but it's a 2D environment
Mhm.
with
So it's
like
a movement based then. How much space that the actor can move in. Is that what the total space is? I'm
yeah,
guessing.
yes,
Okay. It can move 160, let's say, pixel length up
yeah,
and then 210 pixel on the right hand side. Um, yeah,
yeah,
three would be that's another confusing part. The three, the depth, because there's not a depth in this one.
yeah.
Um,
I
okay.
I think another thing that may help out is that like maybe it doesn't make like this the agent the actor will only be able to go left and right and then shoot, but the
Hmm.
bullet itself will keep on traveling. So even after you shoot your bullet, that bullet has its own state, and
Yeah,
you'd theoretically want to be able to hit something. So you'd want to observe that and with your agent. So you do have that number when you shoot your bullet is like where is your bullet when you shoot it, and it'll be
yeah.
in one of these 160 dimension in uh, this direction.
Okay. No, that's cool. Thanks.
Yeah, great question. So I can do a quick recap of the hands-on. So this collab, you basically in the example, everything is pretty much done for you. Again, you can fine tune hyperparameters, but the since we are now working in a using a neural network, you have to make sure that you have your GPU as in the runtime environment because it took like for me it took 45 minutes to train using the GPU, but sometimes like apparently it'll take 90 minutes for 1 million time steps. And if you the idea is like if you don't use a GPU, it could take like 100 times longer, like 1,000 times longer. So this is where that GPU acceleration is really important, especially now that we're using a neural network. But you start off by just downloading the environment, so RL library baselines 3 zoo and all of its dependencies. You create a virtual display. So that virtual display is we're going to create the three or the four frames and the four stack that we use, this grayscale scale stack. So we do that in the code. You create the virtual display so we can record our replay at the end of the training, and you set your own hyperparameter config YAML file, and you can change a bunch of different steps. Right here, we're training for a million. 1 to the times 10 to the 6 is a million. But you can go even like I feel like if I train this model to use like 10 million steps, it would take 10 times longer. So it took me like 45 minutes, so it would take like 450 minutes. But I tried running with like seeing what are the outputs of different time step values, and this is the one that I've seen like the most like improvement from increasing compared to all of these messing with these other values. But I'd go ahead and definitely recommend when you're going through this, you can try different values, put in a lot of like maybe make have a lot of time steps, change your where the learning starts, the frequency, the gradient steps, the exploration fraction. You can change all of these and see in practice how it really works out. They recommend changing learning rate, buffer size, and batch size, but you can just change all these numbers and see what is the impact on it. And it was really eye opening for me. Like I I'm seeing now that if you have like these big AI companies, like they can turn this time step for their when they're training like their cutting edge large language model. If they have access to this GPU farm, they can do so much more training, have a much more powerful agent, and like a much more powerful large language model. And like it's just really solidifying in my eyes like the importance of that hardware component, because at this point we're limited by the hardware we're using, um, and we can turn anything into any like scenario in real life into like a reinforcement learning environment and train an agent to go and do X task. And I know that's what they do with like robotics, but like this is the unit where I really realized that the more hardware you have, like the more compute power, like the more powerful your agent is. So I definitely recommend giving it a shot, messing with different values. And I only went so far through this Atari scenario, the Space Invaders, but you can just swap out the environment um, and then see some results. But for me, this experience this week was like my first like the first couple. I just felt were like learning the basics, but this is where it's like, oh wow, this is the stuff that 10 years ago people were publishing research papers like AlphaGo goes and beats uh, chess, for example. Like so, this is like very very cool to me. And with that, that's all I had for this week. Do you guys have any questions?
Not for me, Blaze. Thanks for doing this. Yeah.
Yeah, of course.